morning everybody. Let's start first order series radioactive decay. We had already covered lot of portion of radioactivity and mathematics related to it. Now this is the process. Here we can observe a series decay, A giving you B and B further decaying into C. Now A decaying into B, this is also first order with decay constant lambda 1. B decaying into C, this is also first order with decay constant lambda 2. Initially we have got some n0 amount of A, 0 amount of B and 0 amount of C. Now this is called first order series radioactive decay. Now we need to analyze this phenomena. A giving you B, this is a normal first order decay. You very well know how this A would vary with time and what would be the differential equation for A and what is A after time t. The more interesting is how B varies with time. What is the differential equation that describes the variation of B? What is the maximum value of B when B would be maximum? And how C varies with time. Now, let's start this. For A, we always know that it's a first order decay minus dA by dt. The decay of A, since A is decreasing, has minus dA by dt is lambda 1A. This is very well known equation for the first process, and you always know the solution of this equation. A is n0 e to the power minus of lambda 1 t. This is the variation of A with time and it's called exponential decay. A varies with time. It's like this. Initially at 0 time A is n0 and this exponential decay will have half-life of ln 2 by lambda 1. This is well known to you. Now here we are more interested in this B. For this B, one can always say B varies according to two paths. This is path 1 through which B is forming, and B also varies through path 2 through which B decays. For this B, one can always write dB by dt. Overall dB by dt would be dB by dt through path 1 plus dB by dt through path 2. This is a very basic differential equation. If any quantity varies according to multiple paths, the variation of that quantity with time would be equal to the sum of variation of that quantity according to the sum of all those paths. So dB by dt is equal to dB by dt through path 1 plus dB by dt through path 2. Now through path 1, let's try to understand this. dB by dt through path 1. Through path 1, B is increasing, it's forming, and the rate of formation of B is same as the rate of decay of A. So dB by dt through path 1, I can always say it's minus of dA by dt. The amount of A that decreases is equal to the amount of B that forms through path 1, and minus of dA by dt is lambda 1A. So this is dB by dt through path 1. Now, what is dB by dt through path 2? dB by dt through path 2. Through path 2, it's a first order decay of B with a decay constant of lambda 2. So I can always say dB by dt is negative since it's decreasing. Decay constant is lambda 2 and it's first order decay, hence it's equal to lambda 2B. B is amount of B at any time t. This is dB by dt through path 2. Now, dB by dt through path 1 is written here, dB by dt through path 2 is written here. I can always substitute the two values here. Overall dB by dt is, dB by dt through path 1 is lambda 1A and dB by dt through path 2 is lambda 2B. Now this is an important differential equation which describes the variation of B with time. How B varies with time is always described by this differential equation. We need to solve this differential equation in order to obtain the function of b with time. What would be the value of b after any time t? What is the initial value of b and what is the value of b after infinite time at any time? Now, observe this. dB by dt, and here we have got lambda 2b. And here we have got lambda 1 and a. A is also a function of time. In order to solve this differential equation, first of all, let me collect all the terms of b on one side. I'll rewrite the differential equation like this: dB by dt plus lambda 2b equal to lambda 1a. Now, after writing this equation like this, we need to think of how to solve this differential equation. Observe this term dB by dt plus lambda 2b. Whenever we observe such a type of terms in a differential equation, we always devise a function, and that function looks like this. I'll write that function here. A function in terms of b and t. B is a variable and time is variable, is equal to b e to the power lambda 2 t. See this? This is lambda 2 and b. b e to the power lambda 2t. Now observe this function. I differentiate this function. df by dt. Here we have got two variables. B is a variable and time is variable, hence e to the power lambda 2 is another variable. We have got product of two variables. If I differentiate it, I'll keep the first function constant. I'll differentiate this, and its differential is e to the power lambda 2t into lambda 2. Then I'll keep e to the power lambda 2t constant, and I'll differentiate b dB by dt. This is the differential of this function. I'll simplify it. df by dt is equal to e to the power lambda 2t is same throughout. In the bracket, I'll be left with lambda 2b plus dB by dt. Now observe this. dB by dt plus lambda 2b. I can see this term here, and I can substitute the value of this lambda 2b plus dB by dt here. How? For this, I'll write e to the power minus of lambda 2t into df by dt. This is dB by dt plus lambda 2b. E to the power minus of lambda 2t into df by dt is equal to lambda 1. And for a also, I'll write the value of a. It is given here. N naught e to the power minus of lambda 1t. Now this is a simplified differential equation in terms of time, and one can always rearrange this differential equation like this. df is equal to lambda 1 n naught e to the power minus of lambda 1 plus lambda 2 t into dt. One can always integrate this differential equation. Here we have got df and here we have got a function of time. I can always integrate this function. Lambda 1 n naught is a constant. And while integrating, the limits must be at 0 time and at any time t. At 0 time, let's try to analyze the value of this function. This is the function. At 0 time, t is 0, e to the power lambda 2t would be 1. While at 0 time, b is 0. Hence, the value of this function is 0 at 0 time. And at any time t, we will have some value of b, we will have some value of e to the power lambda 2t. I will say at any time t, the value of this function would be b e to the power lambda 2 t, the function itself. Integrate it. Integral of df is f, upper limit is b e to the power lambda 2 t minus 0. Thus, integral of left hand side, right hand side, lambda 1 n naught e to the power lambda 2 minus lambda 1 t upon lambda 2 minus lambda 1, and time goes from 0 to t. There is the integral. Now, I can rewrite b e to the power lambda 2 t is equal to, here lambda 1 n naught upon lambda 2 minus lambda 1 and e to the power lambda 2 minus lambda 1 t minus 1. Simplify it for b and you will get this value of b. b is equal to e to the power lambda 2 t. I can transpose it here and it looks like this. b is equal to lambda 1 n naught upon lambda 2 minus lambda 1. Into the bracket we'll have e to the power minus of lambda 1 t minus e to the power minus of lambda 2 t. This is the variation of b with time. See the function. If one plot for b versus time, how b varies with time. Variation of b with time. Observe that b is 0 initially and ultimately b decays into c. So at infinite time b also becomes 0 once again. While intermediate b is formed when a decays into b. This particular equation would give variation of b like this. At 0 time b is 0, at infinite time b would become 0, while at some intermediate time the value of b will take some maximum value. We'll have some b max at some time t naught. Observe this variation of b with time. Now, the another question is, what is the maximum value of b and when b will take that maximum value? In order to solve this, let's once again analyze. First, note it down and move on. Now, we had obtained the function of b with time. We had plotted a graph how b varies with time. And now the interesting question is, what is the maximum value of b and when b will take this maximum value? In order to solve this situation, we always know that when b is maximum, for b max, dB by dt must be 0. When b takes the maximum value, dB by dt must be 0. Its variation with time must be 0. So, in order to get the time of maximum b, one can always differentiate this function dB by dt, which is, this is a constant, lambda 1 n naught, lambda 2 minus lambda 1. So, I can write d by dt of e to the power minus of lambda 1 t minus e to the power minus of lambda 2 t must be 0. So, I differentiate it, minus lambda 1 e to the power minus of lambda 1 t naught plus lambda 2 e to the power minus of lambda 2 t naught is equal to 0. T naught is the time at which the b will take the maximum value. In order to solve this, e to the power, this lambda 2 e to the power minus of lambda 2 t naught is equal to lambda 1 e to the power minus of lambda 1 t naught. Rearrange it, e to the power lambda 1 minus lambda 2 T naught is equal to lambda 1 upon lambda 2. Or take natural log on both the side, lambda 1 minus lambda 2, T naught is equal to natural log of lambda 1 by lambda 2. Or T will take maximum value when its value is T naught, and that T naught is given by this 1 upon lambda 1 minus lambda 2 into natural log of lambda 1 by lambda 2. This is T naught when B is maximum. This is for B max. Now, what is the maximum value of B? In order to get the maximum value of B, as we know that dV by dt is 0, I can substitute this here. dV by dt is 0. For B max, lambda 1, I can write this value of A must be at T naught minus lambda 2 B max is equal to 0. When B is maximum, dB by dt is 0. When for B maximum, dV by dt is 0. Here I substituted 0, dV by dt 0 is equal to lambda 1 A. A will take the value at time T naught because B is maximum at T naught minus lambda 2, and here B is maximum. So B max can be written as lambda 1 upon lambda 2 A at time T naught. And what is A at time T naught? I can write this value here. B will take maximum value at lambda 1, maximum value of lambda 1 by lambda 2, A at T naught. A at T naught is n naught e to the power minus lambda 1 of T naught. Substitute the value of T naught here and get the maximum value of B during this radioactive decay process. This is a very interesting situation, how B varies with time, what is the maximum value of B, and what is the time at which B will take the maximum value. After infinite time, C would become equal to n naught. One can always write the function for C. The function for C would be C at any time t would be initially A minus the remaining amount of A minus the remaining amount of B. So it should be equal to A naught minus A minus B. This is the variation of C with time. One can always write this equation and not as a constant. For A, we know the function. For B, we know the function. One can always write the function for C with time. Observe it, put it down.